Our group will be presenting the Fpga Lab 1 presentation. This is prepared by me, ZHARFAN, Akmal and MIOR HAZIM. The table of contents for this lab is the introduction, method and flow diagram, code explanation, result discussion and lastly the conclusion. So for the introduction, you can see here the Altera board. The DE2115 offers the software support for common I/O and a control panel capability for accessing various components, in addition to these hardware features. Next, you will see the block diagram for the Altera. The Cyclone 4E FPGA device serves as a conduit for all the connection to give the user the most freedom possible. As a result, the FPGA can be configured to implement any system architecture. Next is the two components that will be introduced in this lab, which is the half adder and the 7-segment counter. The half adder produces output in the form of carry and sum after adding two input digit, 1 bit value. So you can see here the A and B will be the input and the carry and sum will be the output. Next, for the 7-segment counter, each segment has 7 light emitting diode LEDs, which can utilize collectively to create one whole digit on the display. You can see the schematic diagram for the 7-segment counter. The objective of this experiment is to understand the basic design flow by using the DE2115 box and Quartus 2 software. The second one, to design a simple full adder with VHDL, a schematic block diagram and waveform. And lastly, to design a counter with a frequency divider by using the 7-segment on the DE2115.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Akmal and now I will present about method and flow diagram. For the first task is to create half adder. For the first step, the software is open and new project in the wizard is created. For the half adder, the VHDL description is written and then compiled completely. Next, after the compilation process is finished, the schematic block diagram for the half adder is created as you see in the window. And finally, the output waveform will be displayed and the result is recorded as we shown in the result later. Okay, next for the task 2 is to create the 7-segment counter. Okay, first to create the 7-segment counter, we need to follow from the given picture here. Okay, from the given picture, we need to create the divide 10 and the divide 15 of VHDL description by using the VHDL description that is given in the lab sheet. Next, then design the clock gen by using the VHDL description also given in the lab sheet. Okay, for the next step is to compile together the clock gen, the divide 10 and the divide 15 into the schematic block diagram of the clock gen. The schematic of the block diagram is designed by referring to the figure that is provided in the lab sheet. Next is to design the clock counter from the VHDL description that is given in the manual. For the next part is to design the stack deck, which is the 7-segment VHDL description language, also given in the lab sheet. And finally, to program the count 0099, all of the a program which is the divide 10, divide 50, clock gen, SecDec, and the clock counter is compiled together before program to the count 0099 by using the description that is given in the lab sheet. Okay, and finally the output of 7 segment is observed and will be shown in the result later.
Next, we proceed with the code explanation. So the coding start with the half adder. The library IEEE and the use IEEE.std logic 1164.all will be declared, and of course the design entity will be declared too. For the entity, the port A and B will be assigned to the input, and the sum and carry will be assigned as the output. And for the architecture, the sum will be getting the value A, X or B, and the carry will be getting the value A and with B. Next is for the divide time. The library and the use IEEE will be declared, and the entity divide underscore 10 is, so port input port will be the clock in, and the output port will be the divide 10, and it ends. For the architecture of divide underscore 10, the signal B will be the integer range from the 0 to 10. So it begins the process. The process of clock in begins. So you can see here the clock in event and clock in equal to 1, which works together so that the tool can identify the rising and the falling clock edge. So the value B will be assigned as the B plus 1, and if B equal to 5, then the divide 10 will be 1, or else if B equal to 10 and divide 10 will be 0, and hence the B value will be 0, and it ends. Next, for the divide 50, it actually use the same concept with the divide 10, but only change with the device to the divide 50, and the B value, the signal B, will be the integer range from 0 to 50.
For clock-gen coding, it start with the library declaration, and then for the entity part, it was named as CLKgen, and CLKgen has one input port, which is CLKin, and 6 output ports, which are F10 Hz, F1 Hz, F100 Hz, F1 kHz, F10 kHz, and then lastly F100 kHz, which are all type standard logic. And for the architecture, it was named as BDF type. It contains two component declarations, which are divide 10 and divide 50, which are both are divide by end counters. It also has six signals synthesized via 0 to synthesized via 5, which are used to store intermediate values and interconnect the components. The architecture also has several instances of the component divide 10 and divide 50, and it interconnects them using the port mapping. The first divide 50 components take the input clock CLK in as input and divide it by 50. The output of this is stored in synthesized via 0. Then the output of synthesized via 0 is passed to the first instance of divide 10 component, which divides it by 10. The output of this component is stored in synthesized via 1. This process continues to the next instance of divide 10 components, where each component takes the previous output signal as input and divides it by 10 and stores it in the corresponding signal. Finally, the last output signal, synthesized via 5, is assigned to the output port F1 Hz. Right, for CLK counter coding, first we declare the library use as same as before, and then for the entity we name it as CLK counter, and then we define the port where CLK again is the input port and SKU as the output port. And for the architecture we name it as A, and it contains two signals B and X, which declared as standard logic vector and standard logic respectively. The architecture also has a single process P1, which is sensitive to the CLK in input. the process P1 runs when there is a change in CLK in. Inside the process, it has an if-else statement. The if statement checks if the change in the CLK in signal is a falling edge by checking CLK in event and CLK in equal to 0. If this condition is met, it increments the value of the signal B by 1. After that, it has another if-else statement which checks if the value of B is equal to 9. And then if it was true, then the value of B is equal to 0, 0, 0, 0, and it assign the value of B to Q, the output port. And then if the values of B is not equal to 9, it assign the value of B to Q directly. Alright, for setDEC coding, it first declare the library used, and then the entity was named as setDEC, and C is declared as the input port, and H0D as the output port. The architecture was named as A, and it contains a single process that is sensitive to the changes of the C input port. The process starts at which compares the value of the input C to different case values and assign a corresponding value to the H0D. It compares the value of C with different case, and based on the value of C, the process assign the value to H0D. In case of the value of C is 0, 0, 0, 0, then H0D will be assigned with 1, 0, 0, 0, 0, 0, 0. And when C is equal to 0, 0, 0, 1, H0D will be assigned with 1, 1, 1, 1, 0, 0, 1, and so on. In case of C has other values, then H0D will assign with 1, 1, 1, 1. The process runs every time there is a change to the input C, meaning that if the values of C changes, the process will be re-evaluated and the value of H0D will be updated accordingly. And this SHARMARAO coding, it use a case statement as the process statement.
Okay, for the next part, the figure shows the count 0099 coding. The counter will count from 0 to 9999. The process will begin when clock 10 receives input from the clock in and justify the frequency to 100 Hz as clock input. Then the frequency will change to other values such as 1 Hz, 1 kHz, 10 kHz, and 100 kHz. In line 47, we change the frequency to get a difference of counting speed. When the frequency increases, the counting speed from 0 to 9999 also increases.
So for the result task 1, we will be getting the half adder waveform as shown here. So if let's say we will take the input A and B equal to 0, the sum and carry equal to 0. So we compare from this waveform. If A and B equal to 0, then C and S equal to 0. Then we try to take another one, the 0, 1. The sum and carry will be 1, 0 respectively. So you can compare from this to when the value A equal to 0, B equal to 1, the sum will be 1 and the carry will be 0. So hence the result we obtain is correct. Next, we will be getting the block diagram of the half adder. So you can see here the input A and B will be XOR and AND to get the value of sum and carry out as the output.
Alright, next we move to result for task 2. Alright, for this one is the block diagram from ClockGen. This block diagram was produced after simulate the ClockGen coding in the Quarters 2 software. After that, we arrange the block diagram according to the lab manual. As you can see here, CLK in act as the input, and the divide 50 block and divide 10 are the component that was indicated in the architecture design. The output of this block will be the input of the next block, and this cycle was going on until the last block where the value of this output will be assigned to the F1 Hz port. before we upload the count 0099 coding into the board, we need to assign location to these nodes, and we got the location from the user manual given in the goals. And then this figure shows the variable layout after we finish to assign location to each of the nodes given.
Okay, this is the result of 100 Hz. Okay, for the next part is the discussion. There is 3 questions in this part. So the first question is what is happened when the implementation of the counter at high and low frequency clock, and here we will show the output in the 7 segments. This is for the high frequency, which is the frequency of 10 kHz. The clock counting is the 7 segment counting is very fast. This is for the low frequency, which is frequency 1 Hz. The counting is very slow, as you can see in the video.
For the next one, explain why the component instantiation and the process statements are used in count 0099. So a component instantiation statement defines a subcomponent of the design entity in which it appears, associate signals or values with the port of that the subcomponent and associate value with the generic of that subcomponent. If let's say we take one line from the code count 0099, U2 set that port mat, C is assigned to Q0 and hex 0 underscore D is assigned as the hex 0. So from this, a port mat tells that how the design entity is connected in the enclosing architecture. So since the component instantiation segment are concurrent statement, an event on any signal associated with the design entity's input in its port mat causes the design entity to execute. So for the next process statement, so meanwhile, VHDL's sequential statement can only appear inside a process statement or the subprogram. So as a result, when reading a program, it is easy to determine from its location whether a statement is concurrent or sequential. So a process statement is actually a concurrent statement that contains a sequence of sequential statement. So to conclude that, the process statement in count 0099 made the system to able in examining the output of the process without learning any of the sequential statement first port mat.
Alright, we move to the third question. The question is explain the process statements inside that and CLK counter. Inside that process coding, it uses case statement and acts as a conditional statement in which a selection is made based on different values of a particular variable or expressions. Based on the code, C is the sensitive components. It compares the value of C with different case, and based on the value of C, the process assign the value to hex 0D. In case of the value C is equal to 0000, and then the hex 0D will be assigned with 100000, and when C is equal to 0001, hex 0D will be assigned to 1111001, and so on. In case the C has other values, then hex 0D will be value of 111111. The process runs every time there is a change on the input C, meaning that the value of C, if the value of C changes, the process will be re-evaluated and the value of hex 0D will be updated accordingly. For CLK counter coding, I use if-else statement where it is a sequential statement in VHDL and go executed depending on the value of the condition. The if condition tests each condition sequentially until the true condition is found. and if a statement could also be treated as the decision-making statement, and the statement associated with it could be a condition. So in this case, P1 is sensitive to the CLK in input. The process P1 runs when there is change in CLK in. The if statement checks if the change in the CLK in signal is a falling edge by checking CLK in event and CLK in is equal to 0. If this condition is met, it increments the value of the signal B by 1. After that, it has another if-else statement which checks if the value of B is equal to 9. Then it resets the value of B, which is 0, 0, 0, 0, and assign the value of B to Q. And then else, if the value of B is not equal to 9, then it assign value of B to Q directly. Alright, we move to the last part, which is conclusion. In conclusion, the objectives set for this project were to understand the basic design flow of using the DE2-115 board and Quarters 2 software to design a simple half adder and a counter with a frequency divider. The full adder was implemented using VHDL, schematic block diagram, and waveform, while the counter was designed to utilize the 7 segments on the DE2-115 board. Through the project, the understanding of basic design flow and the use of the board and Quarters 2 software was achieved, and the successful implementation of the full adder and counter circuit verified the understanding of the VHDL language and circuit design principles. Another thing that we have learned throughout the lab sessions is the effect of the frequency clock towards the speed of 7-segment display. High value of the frequency clock will make the 7-segment come faster. During the lab session, we faced few difficulties during the lab session, such as we cannot to upload the COUNT 0099 coding into the DE2-115 board, and the problem is settled right away by setting the hardware setup and select the USB blaster as the medium. Lastly, this project served as a foundation to move on to more complex designs and further deepen the understanding of FPGA design. I think our presentation has come to the end. Thank you very much for your attention.